Okay, sure, it's no problem. That's not what I got. That's something else. Yep. Where's the list? Do you put value back? I seven is easy. It's 7. And there's there in the bottom of the ladder, 7 feet into the wall.
Alright, well then, okay, well, we haven't put twisted value for Y.
For Y, I got 24. Square. That's square, that's 25, minus what you did divide it. You did divide it, 49. 24. Boston, you're skipping by. Yeah, of course. Of course.
Yes, and you're skipping by. Crazy.
Okay, let me just walk through number 1 here. This is one of the first really raised problems that we learn how to do with Pythagorean theorem. So a squared plus b squared equals c squared, and we find the derivative. All 6 variables will show up in our derivative. So we list them out: x, y, z, dx dt, dy dt, dz dt. 25-foot ladder, that's going to be your z value. The ladder is being pushed towards the wall, so the direction doesn't matter. It's the fact that this horizontal length is decreasing over time. So we want to account for that by calling the dx dt a negative value, indicating that there's a decrease in length as time passes. dy dt is what we're looking for. How fast is the top of the ladder moving? And the remaining pieces that we don't know is dc dt and dy dt. In this case, because of the fact that the ladder is going to stay the same length the entire time, that's why we know dc dt is 0. And then for y, we can use Pythagorean theorem: a squared plus b squared equals c squared. I got a handout you guys can pick up. So 7 squared plus y squared equals 25 squared. Use your calculator. You get y equals 24. And then now it's just pretty straightforward. Plug everything in. Got a handout for you guys want to pick up. dy dt is a positive value. That should make sense because as we push the ladder up against the wall, you can imagine it's going to be sliding up the wall, causing the y vertical length to increase. Okay, if you guys are joining online, then I have the worksheet attached to yesterday's remind. Number 2 is also the Pythagorean theorem problem. If I were to give a problem like that, like number 2, I would draw the diagram for you. You wouldn't have to figure out the diagram on your own. So the diagram would be drawn, but it's another Pythagorean theorem problem. But now all your, so as the car is nearing towards the intersection and the train is moving away, the difference here is that all three variables are changing. So it's not like the ladder problem where one is holding constant. Y is decreasing, X is increasing, and then Z is changing as well. So because of what we understand about this diagram, we know that dy dt should be a negative and dx dt should end up being a positive. In this case, they're telling us dz dt is a positive, but we have to make that determination that dy dt is negative. As the car nears the intersection, causes this vertical component of the your triangle to be decreasing. And the rest should be pretty straightforward. If you have two sides of a right triangle, Pythagorean theorem can help you find that third side. And the rest we can just plug in. Let me know if you have any questions about any parts of the setup for number 2.
If we get decimal, do we just do like the?
Yeah, 3 decimal places. I think that's the standard rule for AP exams as well. For decimals, 3 decimal places. Part B, at what rate is the area of the triangle changing? So area of a triangle, in this case, my area is 1/2 base times height. My X and Y represents the base and the height of the triangle. And this one, we're going to have to need product rule to get through. So F prime G plus FG prime. But once you get through product rule, the rest can plug in nicely from all the values that we found from part A. And then careful with your units of measure. Area is in terms of meters squared, and time is in terms of seconds. As after part B, I want you to skip to that third page, and let's do part C for this problem. That way we can, because it's all connected, but I didn't get to print that out till later. So page 3, same diagram, but now we're trying to find d theta dt, and d theta, and theta is in between y and z here. Any trig function can work. I just like to use tangents. A lot of times that just usually what's given to me is in terms of x and y. So I like to use tangent, but if you use other trig equations, I think all can work because we have enough data to do all of it. But just to let you know, I worked it out in terms of tangents. Anybody have any questions? Number 2, A or B? Okay, this is number 2, part C. Okay, at what rate is the change of the angle? At what rate is theta changing? So same diagram, and diagram will be drawn for you, so you won't have to figure out where that theta is. So I'm going to use tangents. So tangent is x over y, and because they're both variables, I have to go through quotient rule on the right side. and then tangent becomes secant squared theta, d theta dt. So all the values on the right side should be everything that we pulled from the previous parts. So we can reuse all that data. The thing we have to be careful about is sometimes students feel like they want to get to theta, but we're not going to find theta. We're trying to find secant of theta. So we're going to draw a second triangle with all the sides filled in and see if we can find a ratio to replace secant of theta with. Yes. It is, but for the way that I drew it, I had an x over y, opposite over adjacent. Yeah. But if you had to find your variables other in another way, then it could be y over x. So the unique thing about trig related rates is finding that replacement for that trig function. And so this is what the second triangle looks like with the sides filled in. And then secant is is a hypotenuse over adjacent because we know it's a reciprocal of cosine. Cosine is adjacent over hypotenuse. So therefore secant is hypotenuse over adjacent. And then we should be in the clear. Now everything we all have just numeric values in front of us, and we're just trying to get d theta dt by itself. Okay, moving on to number 3. Does anybody still need to look at number 2, part C? Okay. So number 3, if you find the derivative first, just get that out of the way, and that way you can have all the equations that you need in front of you. And then you can just start to decide where the pieces fit and how you want to do substitution with values to eventually make your way down to your answer. So starting off with derivative here, v becomes dv dt, 4/3 pi stays, r cubed becomes 3r squared dr dt, s becomes ds dt, 4 pi stays, r squared becomes 2r dr dt. If we do some cleanup, then we have equations for dv dt and ds dt, as well as volume and surface area. dv dt is 40 because we see the volume is increasing by 40 cubic feet per minute, so we know it's going to be a positive 40. How fast is the surface area increasing? We're looking for ds dt, and the radius is 5. Okay, so now all the calculus is done. We're just having to use the appropriate equations to help us get to our final variable. So we're looking for ds dt. So ds dt requires r and dr dt. Well, r is ready for us to use. That's good. But we don't have dr dt, but we do have dv dt. And so there's our link there. If we can replace dv dt with 40, replace r with 5, that will allow us to get to dr dt. And if we have dr dt, then there's our last piece that we need to get to ds dt. So we're just substituting into equations until we eventually get to the variable that we're trying to solve for. Our units of measure, surface area, focus on that word area. That's a two-dimensional unit. So that's going to be square feet. Time is in terms of minutes. So square feet per minute is our unit. Notice that when you solve for dr dt initially, that pi is in the denominator. So if you plug 40 divided by 100 in the calculator, that's fine. But just make sure you leave that pi out of the calculator and then make sure it's in the denominator that we can hold on to our exact value. So if I'm going through this a little fast, just let me know what parts you want me to explain or go over. Yeah.
Do the pi's and the DSDT, do they cancel out?
In this case, they do because the pi's in the numerator, pi's in the denominator. And so that's why they cancel out. But it just depends on the problem. Sometimes you're gonna have a pi left over. Sometimes they cancel out, so it just depends. Okay, I'll work number 4 from scratch. So I think cone problems are the most algebraically demanding. That just has so many steps involved. So, but any questions with 3? Okay, that's as far as I want to go. Initially, I don't know whether to solve for R or H yet. So let me go back and look at the problem here. The cup is being filled with water at a rate of 19 pi over 5 cubic centimeters per second. So cubic centimeters, that indicates we're talking about volume per second. We know it's time related. This must be dV over dt. Water's cup is being filled, so our volume is increasing, so positive rate. How fast is the water level rising? So we're looking for dH dt. When the water level is 20 centimeters, so when H is 20. And careful with that H equals 20. We don't want to use this too soon. It's a moving value. We want to hold on to our variable. So this we want to save until after derivative.
Explain, how you know, solve for either H or R.
Yeah, so the big hint is that we're looking for dH dt. So we prefer to have our volume equation in terms of H, because H will just naturally produce dH dt when we do the derivative. So, and because we're looking for dH dt, we would like to get our R variable to go away. So if I want my R variable to go away, I want to solve for R so I can find a replacement for R. So again, we're looking for dH dt, so that's a big hint. We would like the radius to go away, so I'm going to solve for R. I mean, you can use 30 H over 70. It's just, if I can reduce it, it'll just be easier numbers to plug in. So this will go in for that R there. So again, the whole purpose is that we want to find the derivative, but we don't want to do product rule. If we do product rule, we're going to have too many variables and not enough information. So we're trying to get our variable down to 1 so that all we need is power rule, and the only thing that's going to show up is dH dt. Now, once you make your substitution, make sure you spend time cleaning up because this is not ready for derivative unless you want to go through a product and chain, and that's too much. It's not worth the trouble to go through that if we can just do a little bit of cleanup and just rely on power rule. I'm merging all the coefficients together. I see an opportunity to reduce, so 9 and 3 becomes 3. And then the h's come together, so h cubed. So this is where we want to be before we find the derivative. If you find the derivative anytime before this, you're making things more difficult. So if you get to this point, the derivative should feel fairly simple. It's just b becomes dv dt. Just do a simple power rule. H cubed becomes 3h squared dh dt. And once you find the derivative, then now you can involve all the values that you want to plug in. It doesn't come out to be an easy fractional value. So leaving it in decimal is fine. Yes.
What would we do if we were given the grading system at the height, but we still had to find the HT?
Yeah, good question. So let's say the height wasn't given to you. Let's say instead it was the radius of the water level. So just for explanation purposes, let's say instead of h, you're given r. So that means when you get to this point, you still need h, you still need the height of the water level, but the problem gives you the radius of the water level. How can we get that into the variable that we want to use? Yeah, use proportion equations. So we have r equals 3h over 7. We can use that to help us convert from one variable to the other.
Thank you.
I got a worksheet, if you want to pick that up. Any questions with cones? In your quiz review, did you guys get a chance to work through? It says page 41 at the top here. I just pulled this from another worksheet. So you'll see a problem with particle motion. So yeah, let's do this one since you're going to see a full page of this as well.
Page one of the morning review, question one for the audience to be, where these roads?
Oh yeah, so this is one of those problems.
Easy.
DCDT. Because of the fact that this is a ladder problem, and you know that ladder is never going to change its length. It's going to stay 25 the entire way through. So that's why the rate of change of that is 0.
Zero.
Yeah, for ladder problems it is. But for part B, you can see that you can imagine that as a car and train is moving, all 3 parts are moving. So you know, in that case, DCDT is either going to be given to you or you have to find it on your own. Yeah. Okay, so if you haven't done this one, I'll just do it with you. So yeah,
Oh, there's those particle problem.
yeah, I think the total distance is built into this one as well, right? So yeah, I think that hopefully I'll answer your question. Okay, so again, this is off of the quiz review packet or worksheet. It says 41 at the top there. Okay, so part A, find the velocity and acceleration. So we're going to go ahead and do that. If it helps, pull that 4 out as 1/4 so that it just feels more clean. Okay, find velocity and acceleration. Just do power rule to get there.
Well, finding the limit of velocity and acceleration would be power rule.
Yeah, yeah. The ones I gave you will be power rule. Okay, fine. When the particle changes direction, so let's create our velocity number line. Let's set velocity equal to 0. Now, if you go back and read the problem here, it says that this particle movement is defined for all real numbers. So that means we don't have it's not just positive numbers. So number line is going to include all negative and positive numbers. So that means we're going to keep -1. Yeah, I'm just choosing test points that I find are relatively easy to plug in. So I'm just taking -2 here, putting into my factor form. So negative times positive sorry, negative times negative times negative, so 3 negatives. Negative 1/2 n, negative times positive, so 2 negatives makes positive. Positive, negative, positive, 1 negative is negative. Positive, positive, positive. And then just so that these test numbers don't distract you, if you just cancel them out so that cross those out so that you know that they're not going to play a role in anything that we do next. We're not going to include them in our interval statement. They're just there to help us get the signs up and running. Okay, so we see changing direction at -1, 0, and 4 from left to right, from right to left, from left to right again. So and the reasoning is because v of t changed signs. Part C is moving left. Part D, I meant to say moving right. Yes, question.
If it didn't say for all real numbers, would you just take out the -1?
Yeah, take out the -1, and then we would just simply start at 0.
Thank you.
Okay, moving left. Okay, moving right. Okay, any questions so far? All right, average velocity. How do we define average velocity? Change in position, good, over change in time. How do we define average acceleration?
Change in velocity.
Velocity over change in time, right? So the tricky part is the words, the function mentioned in the problem is not the one that we use. So we're just doing slope for the appropriate functions. Find x of 1, find x of 3, use your calculator. Your units of measure, though, will still represent velocity, meters over minutes. Average acceleration, find your velocity at 1, find your velocity at 3. But now it's meters per minute, all over minutes. So our units is still going to match what we expect from acceleration, meters per minute squared.
Does it matter where we put the square on the F?
Let's see. Say it again.
Like, does it matter where we put the square?
It does. Yeah, it has to be with the minutes.
Okay.
Yeah. Meters per minute squared. That's right. For E into your position function. That's right. Everybody okay? E and F. Part G, find the particle's displacement. So displacement is defined as final position minus initial position. There's no time component. So some students get these two mixed up, average velocity and displacement. But if you want to look at average velocity, it's just the numerator of your average velocity. So final position minus initial position. And if we get a negative number, that's fine. So, but displacement is in terms of a distance unit. So it's like meters or feet. So If we get a positive number, that just means that we end up to the right of where we started. If we get a negative displacement, that just means that we end up to the left of where we started. Okay, are we okay with displacement? Okay, distance. When you do distance, you're going to gather initially the same information as displacements, but we may need more information than just displacement. So we still want to find x of 1. We still want to find x of 6. But we may or may not include values in between. Okay, we don't want to just choose all the values in between. We only want to choose a value in between if what? If it changes direction. Yep. And the way we can determine change in direction is we go back to our velocity sign line and ask, is there a change in direction somewhere between t equals 1 and t equals 6? Yes. So we include the location at 4. Now, that's the only time we use the velocity function, just to pull that information. Otherwise, everything else is still stored at the position level. Okay. So the position at 4 is negative 31. So being able to gather the information is the first piece. The second piece is knowing what to do with that information. So any questions up to this point? All right. So now you're going to look at your locations from your initial time to your final moments. So we're going to start off at negative 1.75. So imagine you're on the number line and you are standing at negative 1.75 on the number line. And then you're making your way to negative 31 next, because that's what t equals 4. That tells you that's your next destination. And then after you get to this location, you're turning around and you're walking back to 37 on the number line. So you're starting here, you're walking to negative 31, and then you're turning around and you're walking back to 37. All along the way, you're just counting your steps. So to find the distance, the steps that you took between these two, just subtract these two numbers. And remember, everything is positive, right? Because if you're walking, you're counting steps, you're not counting negative, right? You're counting 1, 2, 3, right? So everything is a positive step regardless of your direction. And then from negative 31 to 37, the steps you've taken will be 68 steps. And then in total, the number of steps you've taken, you just add these together. Some students have asked, wait, how do we know that we're not adding these to figure out that distance? Well, that's not what the time tells us, right? The time period tells us you're starting here, your next point is here, and then you end up here, right? If it's not part of your path, then you're not going to include it. All right, are we comfortable with displacement and distance? All right, is speed increasing or decreasing? What do we use to determine that?
Acceleration and velocity.
Good, change. Yeah, we compare signs, right? If both are positive, then speed is increasing. If one is positive and the other is negative, then speed is decreasing. Okay. In this case, velocity is negative, acceleration is also negative. Two negatives indicate speed is increasing. Okay. What about this one here? Is velocity increasing or decreasing? What do we look at? Just acceleration, right? So another way to think about this is velocity increasing or decreasing? It's basically asking, is velocity doing this, or is velocity doing this? And if you think about, oh, that's just asking about slope of velocity. If we're talking about slope of velocity, then that's why it's only acceleration because it's just asking if it's my velocity a positive slope or if my velocity is a negative slope. And because acceleration is positive, I know velocity is a positive slope, therefore my velocity is increasing.
Auto equation on the second page for age. For that distance, did you not include the negatives because it didn't say all your lines?
That's right, because at the beginning of the problem, it says p is greater than or equal to 0. So that's forcing us to start at 0 and doesn't include negative values. Because of the domain restriction. Yeah, so yeah, let me put a linear approximation problem for you to try.
So you put into search.
Okay, let me do a linear approximation and filter solve through a problem. Okay, so number one, we get 0 over 0. That gives us the green light to do L'Hopital's rule. Reevaluate, we get 3 over 11. That's a real number. We can stop. And what if we get 0 over 0 a second time here? And you do L'Hopital's rule another time, right? So each time you do L'Hopital's rule, you got to do direct substitution. You don't want to just keep finding the derivative until you get down to a constant. So we'll make sure that every time you do L'Hopital's rule that you're following it up with direct substitution. Okay, linear approximation. Our function is 1 over q root of x. Use linear approximation to approximate f of 8.04. We want to choose a nice integer value to build our tangent line around. So what's a good integer value for us to use? 8. Yeah. So let's do at x equals 8. You want to build your tangent line as close to your decimal as possible, but also at a convenient spot where it'll be an easy equation. So they're going to plug 8 in to get your order pair, build your derivative, plug 8 in to get the slope, point slope form, solve for y, and then final step, plug in. This is fine, or if you want to get it down to just one decimal number, that's fine as well, so it's up to you. Okay, we didn't do a cylinder problem, but what's nice about a cylinder problem? Yeah, replace a radius with the number and then you can go directly into your derivative. Okay, let me know if you have any individual questions.
So yeah, how do you put fraction on these?
You're not gonna, yeah, you have to put parentheses around. So it doesn't have a nice math print fractional
Okay.
value. So either use an updated 84 or you can use 36.
Give it 36 per dollar. Like 100. I feel like oh.
Or like question yesterday.
Oh my God. Very minimal studying. I did the test or the quiz with you like 3 times.
Yeah.
But the problem was she had all the like water.
Yeah.
Yeah. So. Sure, that's smart.
Yeah.
That's smart.
It's like you have to do like working out and then. I
don't think any of that or positive.
Light source, your channel length actually.
Well, or one of the notes made up. So
Yeah.
that's my point, Nolan.
Your DXCT should be negative. Which the four dy dt to all be negative. Everything will be negative. So it's well, yeah, you're always starting out with information here. You're not finding the derivative. You're getting cleaned up and actually.
Stuff that we were.
Okay, good. First PowerPoint notes 33 slides.
No, I did like 5.
Yeah, once you are, you're not gonna plug anything in. Until you get something.
What were the quizzes used?
And then you plug in and it's one or the other.
And the membrane is like the way.
Yeah, I know, I did.
What is that? And the membrane is like the protein. When they work together, like how protein. From the start from the DNA.
You know that your radius is never changing, so So as soon as you look at radius.
Plug it in.
Plug it in.
And it's like, it's not.
Yeah, I want stuff.
There's like. No. Oh, yeah, it's. And then it's not.
I know about
Two double
these. I literally said that for 30 minutes. No, they're good stuff.
All the same. I need help. Fail. That's why I got. Yeah. Yeah.
We got some time.
But you can watch.
We're gonna do it so much. I'm calling this.
I love you.
If that happens.